Well, hello and welcome to Carnegie Mellon University's Campus Engagement Day. My name is Kevin Collins. I'm a career consultant at the Career and Professional Development Center here at CMU, otherwise known as the CPDC. Joining me is Kate Livingston, another CPDC career consultant.
Hi, everyone.
Today's session is going to feature speakers from programs at the university that prepare students for careers in computer, software, and web technology. Each speaker will have say a little bit about the department or program, and then we'll turn it over to employers for the Q&A. For the presentation portion, please keep your microphone muted, and please save your questions for the Q&A at the end. Thank you. So I'd like to introduce today's speakers. We have Tom Cortina from the School of Computer Science. We have Greg Kesden from the Department of Electrical and Computer Engineering. And finally, we have Jason Howell from the Department of Mathematical Sciences. So Jason, please go ahead and start us off.
Okay, great. I'd like to share my screen if possible. And it looks like I can do that, so that's absolutely great. So let me share my screen. Okay, so let me briefly set a timer here, make sure I don't run over time. So my name is Jason Howell. I'm the Director of Undergraduate Studies in the Department of Mathematical Sciences. And what I want to talk to you a little bit about today are some of the undergraduate degree programs that we have in math sciences and typical coursework that our students take. Then also take maybe a brief look at some common first destination outcomes for CMU math majors. So we're pretty proud of our math program here. We feel like it's one of the better programs in the country in terms of training undergraduates in the mathematical sciences. But you know, just to go over what kinds of degrees we offer one main degree, a Bachelor of Science in Mathematical Sciences. But within that degree, we have 5 different concentrations that students can choose. So there's a few pure math related concentrations and a few applied math concentrations. So for example, our mathematical sciences concentration and our discrete mathematics and logic probably lean to the pure side, although students in those concentrations will take some applied courses. And then the operations, research, and statistics, the statistics and the computational and applied math concentrations lean towards the applied side, in which students will take probably more applied courses than pure, but again, they will take some pure math courses as part of their coursework. We do have a combined Bachelor of Science and Master of Science honors degree program. This program is a 4-year program. So students in this program are actually quite accelerated. They come in and they take, for the first 2 years, most of the math core courses required for their degree. And then in the final 2 years, they take several graduate courses, write a master's thesis, and leave with a master's degree and a bachelor's degree in 4 years. We also take part in several interdisciplinary programs. We've got a Bachelor of Science and Arts program that combines mathematics with any of the schools or any of the schools in the College of Fine Arts. There is a combined Bachelor of Science in Mathematics and Economics, specifically designed to prepare students for graduate study in economics. And then we have a very popular but selective Bachelor of Science in Computational Finance program, which trains students to become quants and traders on Wall Street. Okay. Now, our typical math majors, in terms of the coursework they take a core set of math courses with some very common themes. So there's going to be calculus courses, including multivariable calculus, some discrete mathematics courses, some analysis courses, some abstract algebra, some differential equations, and some probability. So all of our different concentrations will mainly take those courses, but all of these concentrations, how they differ is exactly in what sorts of electives and additional courses they take. So all concentrations do require some math, statistics, computer science, and physics electives. Now, a good proportion of our undergraduates, around 20 to 25%, do take graduate courses at some point during their undergraduate career. These are definitely students that are in our honors degree program, but also several students who are not in our honors degree also continue taking graduate courses while they're here. And most math majors take a problem-solving seminar course. It's called the Putnam Seminar, taught by Professor Po-Shin Lo, who's perhaps one of our most famous faculty members in the math department. And in terms of strengths of the undergraduate program here, things I want to highlight are that we have academically very strong undergraduates in our program. We get several honors graduates per year, and we've last few years, we've had at least one Goldwater Scholar every year. We offer a really good mix of pure and applied math courses in terms of the types of topics that students can learn while they're an undergraduate here. But one of the main keys of our math major is that it's pretty flexible in that we don't have so many course requirements that students can't find time to do other things. So about 60 to 65% of our math majors complete at least a minor or additional major in another subject. And among those, computer science and machine learning and other minors in the School of Computer Science or additional majors are the most popular. About 40 to 45% of our math majors are completing a minor or additional major from the School of Computer Science. Most of these are minors in computer science or additional majors in computer science. And then finally, the upper level math courses, many of which are very challenging, they require very heavy technical and analytic skills and train students as what we like to say are all-purpose professional problem solvers. So, in these courses, these students are going to walk in, they're not going to know anything about the subject, but they immerse themselves in the subject and they learn some of the key ideas and concepts, and then use the theoretical ideas that they've learned to be able to apply those to new problems in that field. And this is, I think, one of the things that students have to do when they graduate and go into any technical field, is be able to apply their knowledge after they immerse themselves in the field, apply their knowledge, and then be able to solve new problems. Okay, so typical first set destination outcomes for CMU math majors. We graduate around 90 to 100 undergraduate math majors per academic year. We just had our graduation on Sunday, and I believe there were 99 math majors receiving undergraduate degrees in the class of 2022. Now, typically we see around 25 to 35% of these graduates pursue further degrees, either master's or PhD degrees, and about 65 to 75% pursue careers in industry directly after their undergraduate degree. Further degrees vary widely. So we see students leave a math major and go into a wide variety of different subjects for their master's or their PhD degree. Some common ones are going to be pure and applied math, finance, machine learning, computer science, statistics. We see students go in to get an MBA as well. Then also PhDs in math or computer science are very popular. In the main industries that we see hire our graduates are going to be IT and software and tech. I mean, that's probably most of our graduates go into that. Then we have a large number that go into finance, and a lot go into consulting. And so we'll see the word analyst in a lot of the job titles for the first destination outcomes for these students. Now, some companies that hire our graduates, you'll see the FAA and G companies in this list. You also see Microsoft. The National Security Agency is one of the world's largest employers of mathematicians. We see consulting companies, and we see finance companies show up a lot. Okay. Some job titles, we see software engineer as well as software developer. Again, the word analyst shows up a lot, machine learning engineer, consultant, trader, operations research analyst, signals analyst, data scientist, and even things like publisher operations analyst. So we've got a couple of minutes left. So I want to take a look at the CMU Career and Professional Development Center outcomes page. So we're going to go to this website that the Career and Professional Development Center actually supports. And what we're going to do is we'll look at masters and doctorates. I'm sorry, we'll remove masters and doctorates from our list, and we'll go here to academic department, and we'll unselect all, and we'll go down to mathematical sciences. Okay. Now, when we look at this list, we'll see that over the last 4 years, from 2021 through 2018, we had 272 graduates. About 57% went directly into employment, a little bit more than that, or a little bit more than 35%, about 39% went on to graduate study. And only a few were still seeking, 5 out of 272. And then the other were about 6 out of 272 in terms of reporting military service or something like that. Now, in terms of the organizations and the job titles, we'll see lots of, job titles such as technology analyst, data science, data scientist, software engineer. Amazon hires our graduates pretty frequently into different positions. Bank of America is another employer that often hires our graduates. We will see lots of different graduates here. And if you take a look again at the Carnegie Mellon University organization, these are mostly master's degrees that students actually pursue. And you'll notice again, we see master's degrees in statistics and data science, computational finance, statistics, machine learning, computer science, but also things like healthcare analytics and information technology, logic, computation, and methodology, statistical practice, data analytics for science, and then doctorates in financial economics, doctorate in computer science. In terms of other employers, we'll just go through the list pretty quickly because I've only got about a minute left here. And we'll go down. Goldman Sachs hires a lot of our graduates, and we see Google hiring our graduates. Jane Street also is looking for talented math majors. And we see a lot of different companies there. So you can explore these first destination outcomes at this website wherever whenever you have some time. And what I want to close with is just please feel free to reach out to me at Howell4@CMU if you ever have any questions about this. So okay. All right, so that is it for me. And please let me know if there's anything I can answer right now.
Thanks so much, Jason. That was great, and there might be some questions at the end. Let me turn it over to Tom. So if you can quit sharing, and there we go. Beautiful.
Okay, can you hear me?
Yes.
Okay. So you'll hear some parallels here between us, math, and electrical computer engineering, probably. So I'm from the School of Computer Science. I'm Tom Cortina, the Associate Dean for Undergraduate Programs. And this will give you sort of an outline of the computer science side of things. And you'll see that there are some parallels between us and math. We are one of the top programs in the country in computer science. And because of that, we get really, really strong students in our programs. And the students in our programs don't just study computer science or some other areas of computing, as you'll see. They do branch out. We do get a lot of our students who go towards Jason, go towards math. We do have some students who study engineering as well. We have students that really look for taking their computing knowledge and applying it to other areas. Now, one thing that's unique about the School of Computer Science is that we have 7 departments within, 7 departments or institutes that are within the School of Computer Science. So we're not just a department of computer science. And because of that, there's a lot of variety of what the students can do. We have over 250 faculty spread across comp bio, CS, human computer interaction. The Institute for Software Research, they focus on software engineering and security and privacy, among some other areas. Language technologies, think of us speaking to computers and processing natural language. And then we also have machine learning and robotics. We also run a program in computer science in our Qatar campus, where we run the same core courses there as well. We now offer 4 majors. So for a while, when I first got to Carnegie Mellon, we were only offering a Bachelor of Science in Computer Science. But as our program has grown, as there's been a lot more interest in computer science, we've not only grown the computer science major itself, but we've launched within the past 5 years 3 more majors. And that's partly due to the size of the School of Computer Science and the resources we have. So we now offer Bachelor of Science in Computational Biology, Artificial Intelligence, and also Human-Computer Interaction, which is our most recent offering at the primary major level. We offer additional majors in those areas as well as robotics. And like Jason's folks there, we have a combined program with the College of Fine Arts as well. We call it BCSA, so computer science in one of the disciplines within the College of Fine Arts. And we also offer a 5th-year master's in computer science, which is sort of integrated with the computer science degree, so students can stay for a 5th year and study computer science a little bit more deeply and do a research thesis as well during that 5th year. There are many more master's programs in the School of Computer Science itself that are sort of standalone that any student can apply to. But though that one, it's on your slide here, is the one that's really tied to the undergraduate program. Besides the majors, we offer concentrations to our School of Computer Science students. So as they're working on their major itself, they can go deeper into a particular area of computer science. And we currently have 11 of these concentrations that are set up. They kind of act like minors, but because the students who are doing this already have a core in computer science, they don't really take introductory courses in these areas. They just dive right in deeply into these areas. And some of these areas, the ones that are starred, are also available, slightly modified as minors for non-SCS students. They may have to take a few intro courses before they can get into the core of those areas. And these are supported, of course, because of the 7 departments and institutes we have in the School of Computer Science. We have lots of faculty involved in these 11 areas. So Jason talked about some curriculum issues. I wanted to bring it up, showing it a slightly different way. What's interesting about our 4 majors is that all 4 of them have almost exactly the same CS core. There's a little slight variations for a couple of the majors. But we start our students with a mathematical foundations course, which actually parallels what happens in math as well. We teach our students some very important paradigms of programming in the first year, imperative and functional programming. And we even introduce parallel data structures and algorithms in their sophomore year, which in many programs would be actually later on. It'd be a junior or senior level course. Our students also get exposed to how computer systems work. And that actually connects a little bit more with electrical and computer engineering as well, Greg will tell you about. And we have a theoretical computer science course to kind of look at computation itself. And on the right, you see which majors are required to take each of the courses. And so we designed it that way in particular, so students have the chance to kind of figure out what path they want to take. And it also shows to you as employers and to universities, when students come out, if they come out with any of the 4 degrees, they still had this solid CS core that we're known for. The difference is when they go into their upper level courses. And there's a lot of text on this slide, so I'll just kind of give you just kind of a high level view. In CS, the students will continue on with algorithms and the major areas of computer science, including programming languages, systems. There's a course in AI. They look at another domain, which kind of ties in with the concentrations, like software engineering, for example, or computer graphics. There's others available. And they're also focusing on their technical communication skills, oral and written communication. AI dives more deeply into AI, of course, with an intro AI course, a machine learning course. They'll study computer vision or natural language processing. They'll go in, then they also have elective categories like CS does, but they're different. So they'll look at decision planning or robotics, another machine learning course, perception and action, and human and AI interaction. They are required to take an ethics course as well. Ethics is an option in CS as well as the technical communication choices. Comp Bio will go into deeper areas of biology and the computational aspects of that, specifically with genomics, modeling, and the students do have a more significant scientific core than the other majors do. And for HCI, they'll do user-centered research and evaluation, interaction design, service design, and prototyping. And they also study a bit of psychology, how people actually use computers. I showed you the concentrations before. CS requires students to do a concentration as part of their major, or they can substitute in a non-SCS minor. So they can take a minor in math, for example, with Jason's faculty, or they can go to French and Francophone studies or economics, or whatever their passion is, whatever they want to apply their knowledge to. The other majors, it's an option, and some of our students actually still follow concentrations even in the other majors. So this is what we tell we've been doing this when we're telling parents of students who are considering coming here for the fall. You know, how are we different? Well, we are a separate college. We're called a school, but we are a college on campus effectively. So we're separate from the College of Engineering or the College of Science, although we work with both of those colleges. We work with Jason, we work with Greg a lot, right, to connect with them. You know, we share courses back and forth. We're very interdisciplinary. That's part of our DNA. And we bring the newest ideas into the classroom. So students tell us when they're taking the 100 and 200 level courses, they're learning a lot more than what their peers are at other universities in those initial courses. We have, just like with math, of course, we have a significant focus on mathematical foundations in our computing courses. It's not all just about coding, but it's all about thinking about using mathematics to support the coding, to give you, especially for AI, or if you're looking at code and trying to determine its correctness, we teach students a lot more about logical reasoning and using that rather than solely testing code by running it. We tell our students to expect to work harder than you've ever worked before, and they always tell us that that is true. So we always give that the mountain analogy. You're climbing a mountain instead of just climbing a hill. But the students are a key part of this whole process, and that's not just for computer science. It's for all the majors you're going to hear about here. The students really help as teaching assistants and as mentors, and they're in a lot of our organizations and our meetings with the dean, and they provide feedback for us as we adjust our curriculum. As we look at the student experience, we're always asking students to be on these committees to help us. We have about 220 to 240 graduates per year. About 15% go on to graduate school, and it's about half master's, half PhD, to places you would expect, you know, including ourselves, of course, as well as some of the top schools in computing around the country. But our students, of course, are aggressively recruited by many of you, by IT companies, financial services, engineering companies, and commerce. A lot of our students end up on the East Coast or the West Coast, although we've found that more students are staying in Pittsburgh than we've had before. And like Jason, I have a link to the dashboard as well. So I wanted to just shift to that just briefly. You know what it looks like already. So I already have it queued up for computer science. And what I did here is I searched for the school of computer science, which captures all four majors, CS, AI, HCI, and Comp Bio. And you'll see here that many of our students go to industry. All right, and this indicates over the past 4 years, we had about 20% go on to continuing ed, which would be a master's or doctorate. The typical, I didn't bother writing on my slides, the job titles, because you're going to see software engineer and software developer a lot, right? As you see that, even if students are in one of the other majors besides computer science, you'll see that. But you'll see some of the big companies that hire our students, that's actually a little bit lower here on the page. Facebook and Google, and Microsoft and Amazon, the places you would expect hire a lot of our students, but there are a lot of companies, a lot of places that hire our students. There are smaller companies and startups. So let's just see if this thing reset. It did reset on me. So I will fix that very quickly if I have a moment to do that. And you'll see that it's just a wide variety of locations that students go to. Okay, Adobe, we have Acuna Capital, so we have financial places that students go to, and this list is quite long. All right, so I'm not going to scroll through the entire list, but you can kind of look at that as you go along. And just like on the math side, as you saw, there are going to be cases where you'll see universities, and those are students that are going on for a graduate degree. So many opportunities, and the students do quite well when they leave our university, whether they're going to graduate school and then eventually going into academia, or if they go straight to industry. They are primed to work together. And as I mentioned, the students are the key aspect of this program. And so the students learn to work together quite a lot in all of our programs, mainly because all of our courses, not just the School of Computer Science, but also in engineering and in the College of Science, are very rigorous. So students learn very quickly. They have to work with other people. So we find that our students, when they go out to industry, a lot of the employers tell us that they're great on teams. And that's because they're used to working together already, right? They don't tend to work alone. That's what I have, actually. So I don't know what time it is, but that's what I have.
That was perfect.
Okay.
Thanks so much, Tom. And last but certainly not least, I want to turn it over to Greg.
There we go. All right, let me get my screen shared here. We've got a bunch of slides. I'm not sure that we'll go through all of them here, but we'll go through a bit of them. So my name is Greg Kesden. I am from ECE. And let's run through here for a minute. So ECE is a really large department on campus. And actually beyond campus. So just in terms of our campus spaces, to provide a little bit of an orientation, there's sort of home base, which is Hammerslag Hall, the space that we've historically occupied. There's a relatively new space with Scott Hall, where we have a nanofab facility and a bunch of other types of stuff going on there. And then in Ansys Hall, it's sort of our very creative space. We have a huge maker space there, large collaborative work areas. It's a very, very modern, student-centered, design-centered, work-centered space. Globally, ECE has programs across the globe: Thailand, Rwanda, Portugal, Pittsburgh, and Silicon Valley. So we're a relatively large program in that sense also. Just by the numbers, so a little bit of an appreciation for the people involved. There are over 1,500 people in ECE, 75 core faculty members, 179 faculty members when you start to count courtesy folks, adjunct folks, and folks like that, more than 100 staff, both technical and non-technical, more than 500 undergraduate students, and more than 650 graduate students. So large department, rich in a huge amount of human wealth in that sense. A lot of different areas of specialization, a lot of different, different things going on. By the rankings, whether you look at computer engineering or electrical engineering, graduate, undergraduate, we're a very, very highly rated program. Anywhere from 1 to 5 on the undergrad side and 7 to 10 on the grad side, depending on how you count it, I think. In terms of mission, the mission is what you'd expect probably from most departments in ECE, right? For most departments of the university, right? We're looking for, for leaders and innovators, right? We're looking to take people who have that technical knowledge, that technical strength, beyond just having that in terms of the technology, being able to actually use that to change the world around them, to understand the society, to understand the world, and to be able to make a difference. That's sort of the core mission. When you talk to people about ECE, people have, different understandings as to what it is. Some people will think like ECE and they'll hear double E and they'll think, a very specific like power distribution, or they'll think electronics and circuits, or they'll think, oh, the space age. Some people hear computer engineering and they'll think, okay, that's the people who build the computers, who design processors and memory systems. And all of those things are certainly really, really true. But the reality is ECE is sort of ubiquitous absolutely everywhere, because everywhere there's, an embedded system, everywhere there's an electronic device solving a problem, that involves a huge amount of ECE. Whether it's you're talking about the software layer on that, or you're talking about the underlying hardware layers, you're talking about the things like the security, and all of that, that's all part of what sort of ECE is. And so we like to talk about like a cell phone, right? As just a way of thinking about all the diversity to what ECE is. You think about a phone, you say, okay, well, it's a phone, right? I talk on it, right? And then you realize, well, it's actually not just an old phone, it's also a computer, right? It's one of those convergence devices. If you look at a cell phone today, it's sort of a computer and a phone. And then you realize, well, actually, it's a computer and a phone, and it's also, wireless. It's a hotspot, right? It's a Wi-Fi access point. And then you realize that actually it does sort of a million other things. It records video, it encodes video, and so on and so forth. And you realize, you look at this device and you think about all the things that it can do, and realize that each and every one of them is actually touched by ECE. Whether you're talking about the radio transceivers used to communicate with a 5G, tower, 3G tower, or talking, interacting with Wi-Fi, or a Wi-Fi hotspot, or Bluetooth, right? Everything that generates and manages that radio is an ECE discipline, right? all the networking support as that becomes part of the internet is an ECE discipline. Once we start to think about recording audio and video and processing that audio video, both in real time for things like our Zoom meeting today, you know, and sort of post-production editing, right? The technology to make that happen and make that happen quickly is an ECE discipline. When you start to talk about machine learning and start to talk about getting that machine learning into a device, things like Siri, that's also an ECE discipline. There are a lot of people involved in machine learning in the cloud, but once we start to say, okay, we need this machine learning in this phone, in this car, in this other thing to actually change the world around us, that becomes a very ECE focused discipline. You start to think about how we do this with energy. And you think about how do we manage that battery power? How do we decide what's most important to do right now and power all the things that we're trying to accomplish to make sure that we can do it with resources available, right? That's an ECE problem. Start to think about that in terms of the Internet of Things and devices that are embedded in the environment. It becomes a really, really interesting problem. Think about things like amplifiers and filters that enable this to work. Think about things like to be able to do, you know, image processing for things like fingerprints very quickly and biometrics, software systems, right? You know, both the operating system level stuff and embedded systems, right? These are part of ECE. You think about actually designing the logic boards, designing the processors, designing those components. Those are things that go on within the ECE space. You start to think about security of these devices, and that's a very, very area that's very, very interesting to ECE folks. Not necessarily the broader cloud security always, but definitely these devices, right? You also start to think about it when you start to think about data centers and start to think about securing the infrastructure. That's sort of an ECE problem, how it is that we build the cloud. And then you get down to the basics of designing things like the processor itself and the memory system and all that. That's all sort of ECE. And then the software stack on top of it. In terms of our approach to teaching, you know, a space this diverse to the students, you know, we have a very strong and broad core with a lot of room to explore above that. And so the students will take a core that covers, you know, electronics and the architecture and the software systems and signals and systems. And that's sort of the basis of the ECE degree, those sort of 4 pillars. And then beyond that, they actually take courses, you know, that build out their depth and breadth in the areas that they're interested in. You know, another, you know, sort of look at it is on this slide, but, you know, we have devices and device sciences, nanofabrication, and circuits that go into the 220 class. Moving from the, you know, the circuits into the signals, that's in 220. Focusing in on the signals, how it is that we actually take data and process it, you know, that's 290. Circuit space, 220, 290, and 240. Hardware is covered in 213 and 240. Software systems, a huge number of courses in that space. You know, in terms of our curriculum, we have a BS degree, we have an MS degree, and we have an integrated degree where the MS is integrated into the BS. A lot of our students continue on for a 5th year. Did my share just disappear? I think my Zoom just.
Yeah, your share disappeared, Greg.
Okay, there's back. Okay. You know, so we have this 5th year, you know, degree. Many of our students choose to do that and hang around basically in some sense for a you know, 2nd senior year, but really a master's degree. In terms of ECE and CS, what Tom just spoke about, a lot of these areas are overlapping in a very very fuzzy or overlapping boundary. And so we can draw circles and we can shade things in and out. But once we start to move into the software space, a lot of this tends to overlap. In terms of things our students do, there are a huge number of student organizations our students participate in. Things that you might expect, you know, in terms of professionally, like IEEE, to things that, you know, that help us broaden our student body and pipeline, support students like WinECE and ECE Outreach. Things that deal with specialized domains like racing and robotics. Built 18 is sort of very, very famous on campus, where students go off, and it's a huge design contest where students go off and build these things using the skills they've developed. It gets a huge amount of industry attention for all the creative and crazy things the students do. In terms of student outcomes, 45% of the students go off from the undergrad program into, you know, industry, About half of them get MS degrees. That half that go off to get MS degrees is heavily influenced by the fifth-year master's program. If we look, most of those master's degrees in turn, probably 90% turn around and convert to students going back to industry. You know, a small percentage get PhDs. Median salaries, you know, about 110,000 for undergrad. I think the average, I guess, for masters is about 120. A huge amount of diversity effort going on. You know, it's very, very important to us that we have a very diverse student body, and that we not only bring in a very diverse student body, but we support everyone really, really well and help each student, you know, succeed. Diversity trends. You know, we're making slow and steady progress. If you look, we haven't had a big step up. You know, I don't know what's going on with my Zoom today. I'm sorry. We haven't had a huge step up in terms of diversity at any one point, but we have had slow and steady progress. Where if you look at these trends, you know, we've really gone from 20% women to close to 40% women, and from 12% underrepresented minorities to about 20% underrepresented minorities. And so we're making very, very steady and continuous progress in the space, and you know, our goal is to keep doing that. In terms of top employers, you know, if you look, software systems looks very big in this picture right now because we do have a lot of software systems graduates. But when you look at folks like Apple, realize that Apple is also a hardware company, and many of the folks that Apple is actually hiring from ECE are actually in the processor space, in the hardware space. And VMware is certainly on that. You know, VMware and NVIDIA are certainly on those boundaries. Where they're going, you know, unsurprisingly, into a lot of the tech hotspots across the country. You know, I think if you look at 2019 to 2021 grads, we had 171 distinct employers and 287 students hired. You know, for that cohort. Tons of research opportunities on campus, ranging from working on the moonshot to working on vehicles to you know, technology infrastructure to security. I think that sort of summarizes, I think, what I wanted to run through. You know, at the end of the day, you know, we're a very, very broad department. We're a very, very large department. We have a huge number of specializations that are under the same umbrella. And just like the faculty, the students get to explore and dive deeply into that space.
Thank you. That was awesome. And thanks to the three presenters, a lot of information, and they had 12 minutes and they all did a great job. So in the remaining time we have, let's turn it over to some questions. I believe there's a number of questions that were posted, and my colleague, Kate, can kind of go through ones that haven't been answered already in the chat.
Yes. One formerly was, there is an ongoing battle between a full stack mindset and a specialization mindset in industry. What route do you feel you best prepare students for? So it's during Tom's presentation, but if anybody else wants to jump in.
So you said a full stack mindset versus a
specialization mindset in industry.
Okay, I mean, I'll take a shot at that. Tom may.
Right, go ahead. You can take it first.
In particular, so you know, so when you look at a job in industry, you know, I think that the philosophy that a company might take between, you know, hiring full stack developers and hiring specialists, and what the balance between those two groups should be, you know, is a really interesting question. And the right balance and the right philosophy probably depends upon on exactly the product and exactly the domain and so on. In terms of how it is that we go about training students, I think there's a lot less tension in how we think about it, because we want to make sure that when our students graduate, our students are oriented, right? Our students have to have, the most important thing that we can convey upon our students, I really think, is perspective. Right. And so we want to make sure that no matter what a student's intended specialization may be or what their role may be, that they have perspective over how the pieces fit together, over what the technology landscape looks like, and how the tools work. And then when, that student may choose to pursue, a whole bunch of classes in a single narrow area, and to go off and become a specialist in that area, and to be hired by a company that hires specialists in that area. Or that student may choose to take a broader set of courses and, get hired by a company who ultimately will train them in a specialization, or continue to use them as a generalist across the full stack or across a breadth of problems. And so I think for us as educators, we try to make sure that even those who want to specialize maintain perspective and some breadth for a really solid foundation, and that those who want to specialize can. That's my take.
Yeah, I'll just add in SCS, the way the curriculum is designed with our concentrations, which are, the CS students have to do a concentration or a non-SCS minor, so they can go off to economics or some other area. It's the same thing as Greg was saying, the students are given that option. The education is set up in such a way that if they really want to go down and become a specialist, like in systems, for example, they can do that, right? And they get credit for that, and it goes towards their degree. Otherwise, they can actually have a broader education if they so choose.
Awesome. All right, one other question, and Tom, you kind of just touched on it in the chat, but wanted to let everyone else have a chance maybe, is just what, if any, techniques are students given to adjust from a problem-solving mindset to an opportunity-finding mindset? Jason or Greg, anything to add here?
So,
I mean, I can jump in a little bit. Okay, Tom, go ahead.
No, you go ahead.
Go ahead, Greg.
Okay, so I think what's a very important transformation at Carnegie Mellon that's occurred since my time here. When I got here in, I guess, 1999, right, there was a little bit of a joke about it being the Forbes Avenue Trade School, that we were the place that really trained the best, the strongest engineers in the world. But no one knew them, right? Because they were heads down, doing engineering. And that it was Carnegie Mellon's goal to transform itself from the Forbes Avenue Trade School to, true societal leaders. And I think over the last, 20 some odd years, we've actually done a really, really good job of that, of making sure that the students understand the world in which they live and care about the world in which they live, and are involved in the world in which they live, and look for ways to improve the world in which they live. Both as technologists and as citizens. And so in terms of that transformation to the opportunity-finding mindset, I think what we really do there is find ways to connect people with the world and with each other, and to understand the journey that various people take through the world and the way they experience the world, and to always ask ourselves, how can I make the world better for this person? How can I make the world better for this group of people? How can I make the world better for everyone? And that view of the world around us, I think, is really now somewhat unique to Carnegie Mellon, and really is what's enabling us to be these leaders, to find opportunities, not just to be specialists in a narrow space, able to optimize within constraints, able to build within specification, but really to figure out what's going to make the world a better place, and what tools do I have in my box to address that.
Great. I believe all other questions were somewhat answered throughout the chat. Thank you, Tom, for jumping in ones that were particular for you in the chat. But any other questions from our employers?
If that's
All
the
right.
case, thank you so much for attending.
We were right on
Tom,
time.
Jason, and Greg did a great job staying within the time limit and presenting just an amazing amount of information. Please, you can always contact the CPDC with any questions you have about recruiting of our students. And with that, I will let folks go to their next things. Thank you again so much.
Thank you all. Take care.
Thanks, everyone.